I guess we're still waiting for Coast people. Oh, it's not even 5 o'clock yet. Oh.
Like as soon as you said that, I looked at my phone and saw it change.
Funny how that works. Okay, this is supposed to be a fresh marker. As in never used before now. Okay. Just needs a little breaking in. Okay. Hi, Leah.
Hi.
Okay, so what I'm going to do, so I have a rather long section in the notes about floating point arithmetic, and I mentioned like the key issues of floating point arithmetic at the end of last time. And what I'm going to start with today is a rather abbreviated presentation of that topic, since only little tidbits are needed for any of the assignments. So if you want more detail, then you can certainly look at that section in the notes. Oh. Hello, Kelia.
Hi.
Okay. Not sure how I feel about this marker. Okay, so where I'm going to focus this is I'm not going to discuss like general floating point number systems. I'm going to focus on the one that computers generally use, which is the
After numbers?
yes.
Then you have
All right, camera control.
a little more. A little more.
I'm increasing my font size, as you can tell by this word. IEEE double precision floating point numbers. So FP, my abbreviation for floating point. Okay. So the way IEEE double precision floating point numbers work is a real number is represented using 8 bytes or 64 bits. So here's how the 64 bits are used. So I'll just focus on this number system, and that will allow me to describe the essential features of any floating point number system. Okay, so I have a grand total of 64 bits. So how they're divvied up is we have 1 bit that's used for the 1 bit that's used for the sign. So means positive, 1 negative. So if this is binary, so all these bits would be 0, 1. We have 11 bits for the exponents. Okay. And then we have the remaining 52 bits are it's stored, what's called the mantissa. So this is where the significant digits of a number are stored. And if you want to think of this, you can relate this to scientific notation, where the significant digits go here, and then that times 2 to a certain power, and that power is represented here. If it just indicates plus or minus. Okay. So the mantissa. So I'll just write this space again. So I need to refer to the individual pieces. Okay. So the sign bit here, I'll just call that S. So S will be 0 or 1. The exponent, that's going to be an 11-digit number in binary. So I'm going to call that B. And the digits of the mantissa I'm going to refer to as D1, D2, D3, and so on, all the way down to D52. So I can use this to describe what real number is actually being represented. So this represents, like if you want the actual value that's stored in these 64 bits. Okay, so x is equal to -1 to the s. So that's why 0 is positive, 1 is negative. Times 1 plus. Okay, you can use remember straight notation, but it'll make sense in just a little bit. 1 point D1, D2, D3 down to D52 times 2 to the B minus 1023. Okay, now there's some things in here that admittedly look strange, but like I said, I'll explain all of it right now. First of all, B is a number between 0 and okay, so 2 to the 11th minus 1, because we have 11 binary digits. And that value is equal to 2047. So what happens is, actually, I'm going to rewrite this so it's not so squeezed. Okay. Okay, so 0 less than or equal to B, less than or equal to 2 to the 11th minus 1, which is 2047. But exponents, we want the exponents to be either positive or negative. We want to be able to represent really large numbers, also really small numbers, close to 0. So what we do is we take the value that's stored in these 11 bits, that's between 0 and 2047, and we shift it by 1023. So as a result, the exponent is now between minus 1023 and 1024 to allow us to represent both small and large numbers. Okay, now, of course, you're accustomed to decimal representation. So, for instance, 1.54 would be 1 plus 5 times 10 to the minus 1 plus 4 times 10 to the minus 2. So any decimal digits are multiplied by negative powers of 10. Here, same idea, except it's binary. So what I'm writing here is 1 plus D1 times 2 to the minus 1, and then D2 times 2 to the minus 2, and so on. Okay. I've run out of board room here. First, any questions about what's up here before I switch to a fresh board? So if I were to write out in a more standard way what that mantissa means, so by 1 dot D1, D2, D3, and so on is 1 plus d1 over 2 to the first, plus d2 over 2 to the second, plus d3 over 2 cubed, and so on. So this is a binary representation instead of decimal. Okay. Now, why the 1? The reason is that in this system that we're using, floating point numbers are normalized most of the time. And what I mean by normalized is the leading digit in the mantissa is not allowed to be 0. So for instance, in scientific notation, generally what you do is you represent a number so that you have, for instance, 2.34 times 10 to the minus 5. You would not do something like 0.234 times 10 to the minus 4 that represents the same number. So it's specified that the leading digit cannot be 0, and that is used to ensure uniqueness. So each number in the floating point system has a unique representation. But there's something nice about binary if you normalize, because your only digit values can be 0 or 1. If you're saying this can't be 0, it has to be 1. You know it's 1. It's the only choice, so there's no need to store it. So basically, by normalizing, we buy ourselves an extra digit of precision in a limited storage space that we have. Okay. Now, there is one exception to this rule, because one drawback of normalizing is you don't have a way to represent 0 exactly. You can make a number that's really small, but 0 itself is not going to happen because you're required to have a non-zero digit. So IEEE makes one exception to the practice of normalizing. That is in the case where the exponent part is equal to 0, so in other words, the exponents is equal to minus 1023. In that case, the numbers are denormalized. So that's one special case. And what it does is that allows you to represent numbers that are closer and closer to 0. So as a result, this means that if all the bits in the number are equal to 0, except for the sign bit, the number that you're representing is 0. So which makes sense, because if all the bits in this, all these 64 bits are 0, you'd think that should mean 0, and now it does. And in fact, you actually have two representations of 0. What's the other one? Minus 0. So I excluded the sign bit. So if the sign bit says negative, but all the other bits are 0, that's still considered 0. So you have plus or minus 0. Okay. Now, so any questions about what the bits mean and how we get a number from them? There's one other exception I need to make note of, and that is, okay, so we have a special case that b is the smallest value possible, 0. If b is the largest possible value, b is equal to 2047, so the exponent is equal to 1024. That is not actually, that is a reserve value. It's not used for actually representing floating point numbers. So your actual largest allowed exponent is 1023, not 1024. This is used for certain special cases like plus or minus infinity. So for instance, if you get a number that's too large to be represented, then the exponent is set to this value, and then depending on the sign bit, you get plus or you interpret it as a plus or minus infinity. Or also NaN. How many of you have seen this in something you've done? Especially if you use MATLAB or Octave. Okay. So, so infinity and NaN are two things you don't want to see. It means you messed up. NaN is called not a number. Mathematically, what it means is 0 over 0. It's an indeterminate form. It can't call it plus or minus infinity. So if you're in MATLAB, for instance, if you type 1 divided by 0, it'll say inf for infinity. Or you could do minus 1 over 0, and it'll call it minus infinity. So it'll try to make sense of what you're doing as best you can. But if you commit an error this grave, then it gives you this, and then you're done for. So, and the funny thing is, your software, whatever you're using, will still try to compute. You'll just have garbage results. So it has rules like what happens if you add infinity to infinity and so forth. Well, okay, so for example, suppose you have two variables whose values are both plus infinity, and your code performs a subtraction. So what should it call that? Infinity minus infinity, how should that be treated? What is infinity minus infinity? What?
Well, the way I think about it is two very large numbers being subtracted, but that doesn't make sense though, because it's infinity.
Right.
Is it
Yeah.
gonna do that?
What?
Is it gonna do that?
Gonna do what?
Do you have?
What are you pointing to?
Confused? Oh, the NaN. Is it gonna get confused?
Yes, it's going to get confused. It's an NaN. No, because infinity minus infinity really is an indeterminate form. So in fact, in calculus, they teach you how to use L'Hopital's rule. If you have two expressions that go to infinity, you can try to do manipulations on it to see what that particular infinity minus infinity is equal to. But if you just have infinity minus infinity by itself, that's an indeterminate form. Whereas infinity plus infinity, if they're both positive, you'd still call that infinity. Because that's something you actually know what's going to happen to it. Because infinity minus infinity could be a regular number. You just don't know. Okay. So now we see the floating point system. It's still using the same 8 bytes. It's just filling different values in there that are interpreted accordingly. Okay. Now, there are certain properties that any floating point number system would have. So I'll go through those. Oh, don't tell me this marker's not going to erase well.
I didn't erase myself.
What? It's a bit more of a struggle than usual. Oh, much better. Anyway, sometimes the rag works better, sometimes plain old eraser works better. Okay. Oh, gotta move this.
Oh, are you gonna? Oh.
Yes. Don't worry. Okay. So I'll describe what these properties are and explain what their values would be in the case of this particular IEEE floating point number system. Okay. So the first is we have, and this is actually the one that comes up in the homework, overflow level. So the definition of overflow is the largest representable positive number. well, I guess we're talking about largest, and it's going to be positive. Those. Now, the way you get the largest number possible is your exponent is the largest allowable value, so that's 1,023. And then your mantissa, to make that as large as possible too, that has to be all ones. So all 52 of those bits are going to be 1. So, okay, so as a result, your sorry, my pages are all messed up here. Okay. So the actual value for overflow in the IEEE case, and I'll only talk about that case, is because of the exponent, we have 2 to the 1023, and then when the mantissa is all ones, so you have 1.11111. Now, just like 9.99999 is, and you cut off at a finite point, that's something that's a number that's really close to 10. So this is going to be a number that's really close to 2. So it's going to be 2 minus 2 to the minus, let's see, 2 to the minus 52. Okay. I have these values right. Okay. Yes. Okay. So this is 2 to the 1024 minus 2 to the 3 minus 52, which I didn't feel like carrying out. But it's close to 2 to the 1024, so a pretty dang large number. Actually, I don't know if my calculator can, right, phone calculator can even handle that. Well, it's using IEEE floating point numbers. So I'll bet that if I, whoops, were to try this, 2 raised to the 1024. Oh, it gives me an error. Okay, so if I try 1 power less, so 2 raised to the 1023, oh, okay, it didn't like that either. All right, so maybe my phone's using single precision. I don't know. So I don't remember offhand. I think it's like a number on the order of 10 to the 308th power, somewhere in that territory. Okay, so you can't possibly represent larger numbers than this. If you get something larger than this, like you have a number that's close to the limit, and when you square it, it's going to overflow, and it'll call it infinity. So this is how close you can get. Okay, on the other hand, at the other extreme, we have underflow. So this is the smallest representable positive number. Now, here we have to take into account that we're doing denormalizing when we talk about really small numbers. So the exponent is going to be minus 1023, and then the mantissa is almost all zeros. So 0.000, and then a 1 at the end. And this is in the 2 to the minus 52 position. So the actual value that we get for the underflow level is 2 to the minus 1074. So MATLAB can represent a number that's small, but if you get any smaller, then it's going to say, oh, it's 0. So this is not really a big problem for computations. If you get a number that's too tiny, the computation can continue because it's so small, you just declare it 0. And yeah, it's pretty small to begin with. So, so why not? Okay. Now, and actually there are commands in MATLAB that give you these floating point number parameters. Like there's real max and real min. those are a couple of commands that actually give you these values so you know what you're dealing with or what your floating point system can handle. Okay. So any questions about overflow, underflow? All right.
Dr. Lambert, so what do you do? So what do we do when we get overflow or underflow? What do we do then?
Oh, well, actually, in fact, this is issue one of the homework problems. If you have a computation that produces that, and if your algorithm is actually correct, then, but it's not supposed to produce that kind of a result, then what could be happening is like maybe some intermediate results are not representable. And so you have to consider like maybe the formulas involved need to be rearranged in some way to avoid computing numbers that big on a way, because if your final result is supposed to be representable, then what happened in the meantime? So in fact, the last problem on the first homework highlights this issue, where the final result's okay, but something happens in the process that creates something too big. But you can try to manipulate around that. And I'll actually show how to manipulate certain formulas to get around these things. Okay. All right. So I need to describe a couple more properties. And I also need to explain, because last time I mentioned catastrophic cancellation, and you need to explain why it really can be catastrophic. Okay. Okay, so other properties of floating point system. One that's particularly important is called machine precision. Well, it's called by many things. Machine precision is a common term, also known as unit round-off. And what it's defined to be is the smallest positive number, bless you, that can be added to 1 in order to get a result that is actually considered greater than 1 in the floating point system. So if you take a number like the underflow level, that number, bless you, and add that to 1, the floating point system is going to think, oh, that's exactly 1. It's not even going to recognize you added something so tiny to it. So the smallest positive number you can add to 1, so it's normally abbreviated as a boldface U. In fact, that's a symbol I use in the notes, and many books use it as well. It turns out to be 2 to the minus 52. And it's 52 because that's how many bits in your mantissa you have. So if you think of your mantissa, you said all the bits equal to 0, except for the last bit that's equal to 1. That is your unit round-off. Oh.
So is that not what underflow is?
Oh, very good question. And okay. First of all, I goofed. It's not 2 to the minus 52. It's 2 to the minus 53, and I'll explain why we get an extra place there. It's 2 to the minus 53 due to rounding. Because when it comes to rounding, so you can either round like we were all taught in school, like in elementary school, where you round to the nearest integer. Or you can chop, where whatever digits need to be removed, you just toss them out, effectively always rounding down. So if you're chopping, then your unit round-off is what I said earlier, 2 to the minus 52. But because rounding is more accurate, you're going from the nearest integer, that buys you, like it cuts your round-off error in half. So we get 2 to the minus 53. Okay. So it all depends on which rounding convention is being used. But at IEEE, rounding is used, not chopping, so this is it. Now, to answer your question about underflow versus machine precision. Now, the underflow level is mainly determined by your exponent. How many bits do you have for your exponent? Now, because we're denormalizing, yes, the number of bits in your mantissa also plays a role, but when it comes to the magnitude of numbers that can be represented at all, it's the exponent that's key. Whereas machine precision is determined exclusively by how many bits you have in your mantissa. The exponent has nothing to do with it. So yeah, a lot of people get underflow and unit round off mixed up, but they come from two separate parts of a floating point number. So for example, suppose I use some other floating point system where I still have 52 bits for a mantissa, and now I only have 6 bits for the exponent. My unit round off is not going to change. My underflow level will. Okay. All right. The last property I need to mention about this floating point system is about rounding. Now, I'm assuming that everybody has been taught rounding the same way as I was like ages ago, but I could be wrong. So for instance, suppose we're taking numbers that have some decimal places and we're needing to round to the nearest integer. So for instance, if you have 90.3, you'll round down to 90. If you have 92.7, you'll round up to 93. What if you have, for instance, the number 89.5? So it's halfway between 89 and 90. How do you round that? Yeah, we were all taught to round up, but it's not done that way here. It's called, the practice that's used for that situation where the number you're trying to round is halfway between, it's called round to even. So what that means is 89.5, if you're rounding to integer. Okay, actually, this is a bad example. You can round either to 89 or 90. 90 is what's chosen. This is what you're accustomed to. However, 88.5, you'd think, oh, round up to 89. No, it actually rounds down to 88. So round to even means you round to the number whose last digit is even. So you're looking at this. And that's how you make your choice. And you think, wow, why do that? Why not just always round? Why not always round up? The reason is to eliminate bias. So rounding practice we've all been taught is statistically biased because of this approach to rounding up. But here we're rounding presumably up half the time and down half the time, so it removes that bias. But yeah, not something that humans could do naturally, I don't think. Okay. And try to.
Can I ask another question about this underflow and the machine precision? I still don't
Okay. Yep.
So, like, if you add, say you have the underflow number and you add that to 1,
Yeah.
Your machine won't be able to tell that it's any different from 1, right?
Right.
So then why, I don't understand, is there ever...
Well, the thing is, this machine precision, okay, so you're talking, a number like I gave earlier, like 2 to the minus 1074. Yeah, that won't register. But the point is, let's suppose I have a number like, in this floating point system, 2 to the minus 100. So that's less than the unit round off. So yeah, if I add that to 1, I'll still get a number, it'll still consider it exactly 1. However, that number by itself, so not added to 1, but just by itself, still registers. It's still something that can be used.
So it's still uniquely not 0. The underflow
Right.
is not 0.
Yeah.
Okay.
Yeah.
Okay.
Okay, so for example, suppose I have a number that's already kind of large, like 100,000. If I add a number like 2 to the minus 49 to that, so it's above this level, but it's being added to a large number like 100,000, it again won't register.
Okay.
Yeah. So it's relative to what your. So the idea is, machine precision is about mathematical operations, specifically addition. If you're working with numbers that have such a large disparity in magnitude, a number gets lost. And this is why, suppose you have a long list of numbers to add, and the numbers vary widely in magnitude. It's best to add the smallest numbers together first, and then work your way up to the larger numbers. If you went the other way around, your sum would be so large that the smallest numbers in the list, you might as well not add them at all. And that could throw off the accuracy of your sum. Okay. Any other questions about floating point properties? All right. See if there's anything else from my pages I really need. Okay. Yes, there it is. Okay, I need to use a symbol and don't hit you. Okay, good. Okay. So here's some notation that's also used in discussion of floating point systems that relates to machine precision. So if x is any real number that satisfies, it's between the underflow limit and the overflow limit, so these are just my abbreviations for these things. So in other words, this is a positive number that can be represented in the floating point system. But the thing is, it won't be represented exactly because we only have limited precision. So FL of x is so this is the representation of x in whatever floating point system you're using. So after x has been rounded or chopped or whatever you're doing with it. And how this relates to machine precision is that the difference between the floating point representation of x and x relative to x, so this relative error, which I'll talk more about later, is going to be at most the machine precision, the unit round off. Okay. So whenever you are taking a number that cannot be represented exactly, like pi or even 1/3, and you get the number in your floating point system that represents it, at least you know this is how close it is to that number in a relative sense. So you can think of this as being like a percentage error. But that's going to be 2 to the minus 53. So, and 2 to the minus 53, I should mention, okay, so this is 2 to the minus 53, which is roughly 1.1 times 10 to the minus 16, just to give you an idea as to how small that error really is. So what that means is, if you are measuring error in your computations, like relative error, you can't expect to get anything smaller than this. It's not likely to happen, just because of all the error that happens in floating point arithmetic. Okay. All right. So now I want to come back to what I mentioned at the end of last time, and that is catastrophic cancellation. Okay. Now, here's something that we all take for granted. Okay, we all know what this is. And of course, this quadratic formula solves this equation, ax squared plus bx plus c is equal to 0. Now, I want to talk about a particular scenario that in floating point arithmetic can actually be problematic with this formula. So what if b is much, much greater than the other coefficients, a and c? Then what happens is this square root of the discriminant, so b squared minus 4ac, is going to be approximately just the absolute value of b. So the roots will, depending on the sign of b, will be approximately equal to, well, one root is going to be approximately 0, and the other root will be plus or minus absolute value of b over a. Because in one case we'll have cancellation up top, and in the other we have b and its absolute value combining. So we'll have 2b or minus 2b up top, and the 2's will cancel. Okay, so and this could actually cause rather erroneous roots. So I'll give an example of how this can go wrong. All right. So let's suppose we have x squared plus 10,000x plus 1. So we go ahead and apply the quadratic formula to that. And we use 4-digit decimal arithmetic. All right, so we're only allowed 4 decimal places, and we're still rounding. And here are the roots that we get. So x1 is equal to 0, we get a root of 0, and then x2 is equal to minus 10,000. Okay, now suppose we substitute these roots into the equation. We plug in the first root of 0, and we get 1 equals 0. So we're a little bit off. In fact, what we'd have to do is, in order to get the roots to any reasonable accuracy, so if we move up to 8 digits, here are the roots we get. So this root that we got at 0 before is minus 1 times 10 to the minus 4, and x2 is 9.9999999. times 10 cubed. Okay, so very nearly 10,000, nearly 0. But the thing is, notice minus 1 times 10 to the minus 4, that's representable. But we still didn't get it. And the reason why is due to this cancellation error. So when we do both signs, a plus and minus, one of these is a subtraction of two large numbers where the result is supposed to be much smaller. And what happens is that subtraction is highly inaccurate, so inaccurate that all the digits are lost. They all cancel out, and we get this erroneous root. So in this case, b is positive. So when we have the minus sign, in this example, we're okay. When we have a plus sign, cancellation occurs because it's an actual subtraction. So what we need to do is try to avoid opposite signs in this situation, and then we'll be okay. So here's what we do is if we multiply and divide by the conjugate, okay, so minus b minus plus, and I write minus plus so that we have a plus here, we have a minus here, we have a plus here. So we go ahead and multiply and divide by that, and then we simplify as much as we can, and what we get is the other quadratic formula, I think. Oh, I think you need the pan. Yeah. And actually, do I need the pan too? No, okay. Yeah, a little more, I need more space out here. Okay. So the other quadratic formula turns out to be minus 2c over b, okay, plus or minus, okay, okay, so what happens is you have to check the sign of b. So what will happen in this case, in this example, b is positive. So what we'll do is we'll use this formula with a minus sign only, and then this formula with a plus sign only. So each formula is perfectly safe for one of the roots. So really, the computers use two quadratic formulas, or any reasonable implementation for computing quadratic roots. It's going to use both formulas because each formula will give you one root safely. So what happens in that case is if we use this formula in tandem with this one, we actually get the correct roots to 4 digits, even with only 4-digit rounding arithmetic. So in other words, it fixes the problem. So this is an example of what you could do to rework a formula that has a risky subtraction in it in order to avoid that catastrophic cancellation. Okay. So any questions about this other quadratic formula? All right. Now, why it's called catastrophic cancellation? Well, I can give an example of how the name came about. I don't know, like historically, who first named it catastrophic cancellation. I'm telling you about a particular catastrophe that happened due to this cancellation. It was the 1991 Gulf War, and we used our Patriot missiles to intercept Iraqi Scud missiles. So in order to carry out the interception, you have to get a good estimate of a trajectory of your target. So what we're doing is we're tracking these Scud missiles. We know their position at various times as a function of time. So we're taking 2 position values, subtracting those, divided by 2 time values. So our velocity is roughly position 2 minus position 1 over time 2 minus time 1. Very straightforward. Now, that seemed to work quite well. We intercepted several Scud missiles. Everything seems fine. But what's happening is these time values that are being subtracted, when you first start doing this, these time values are small, but then they get larger and larger. Unfortunately, the difference between them is always small. So you're subtracting larger and larger numbers, getting the same small results. And so as time passes, this subtraction becomes more and more inaccurate. So what happened on one particular occasion is this subtraction was way off. Thus, the velocity estimate was thrown way off. Therefore, we misgauged the Scud missile's trajectory. Our Patriot missile missed, and the Scud got through, and it killed 28 American troops. So an actual human catastrophe happened due to failure to take this into account. So there was an investigation, and all the documents for this you can find online. And they found this catastrophic cancellation actually caused this missed interception. So what's the solution? What they did was they would restart their tracking equipment every 8 hours. And that imposed a bound on how large these numbers got. And therefore, that imposed a cap on how much subtraction error there was. So then that level of error was deemed acceptable. And that fixed the problem. There weren't any more. So this case of a missile getting through only happened once. So we got lucky that it didn't happen more than once before this was caught. And this sort of thing, like when you're designing a software, you think, oh, this is something that's nice and straightforward. It's mathematically valid. Why should it fail? And because you have to know your floating point system and know all the different sources of error that can creep in. Okay. Okay. Now, speaking of error, I must give a quick word about error measurement. Okay. Again, something that's usually a straightforward thing, but something you still have to think about, depending on the numbers you're working with. So let's suppose that y is the exact value of whatever it is you're trying to compute, and y hat is your approximation. And for now, let's assume that these are numbers. So ways you can measure error, you have the absolute error is y minus y hat. So just the difference between them. Now, you may define this using the absolute value. I've seen this defined differently in certain books. Some leave it out, some include it. However, you might find a more reliable indication of how accurate your approximation is if you use the relative error, so y minus y hat divided by the exact. And again, you may or may not choose to use the absolute value. If you are working with vectors, for instance, or matrices, then these same notions apply, but you use the appropriate norms. So, for example, if I have a matrix quantity, I would have like maybe infinity norm of a minus a hat, and I'm measuring my error that way. So which is best to use? Well, generally, I almost always use relative error. Relative error, you can think of it as percentage error, if you like. So that tends to give you a more reliable indicator of how accurate your algorithm is. But this one is a good idea if the exact value is very small. If you are after some code where you're estimating error and you use relative error, and you get a relative error of 1 or more, that's really horrible. Because if relative error is 1, you might as well use an approximation of 0. So if you get something greater than 1, then you messed up really, really badly. And yes, sometimes I've had that happen. Okay. So, but yeah, if your exact value is kind of small, then it's relative error that can be misleading. So this is just a rule of thumb as far as which kind of error to use. Okay. Now, this next tidbit of error analysis, admittedly, is going to be rather strange. People have a hard time digesting this concept, but I'll give it a shot presenting it anyway. So, typically, you want to find the error in y, where y is a final result of some computation, and that computation had some input. So it turns out that even though you really only care about the error in the output, your input is not necessarily exact. For example, what if the input to your problem is obtained from measurements? There's going to be some error there. And knowledge of that error can be helpful. So this leads to the concept of forward and backward error. By now, even with the absolute relative error stuff, I was into section 2.6 in the notes. Okay. So now your exact value y is a result of some computation, and I'm using just a function to describe this process. So you can think of, so x is your input, f is your algorithm. It could be something very simple, like an ordinary function like you've seen in any other math class, or it could be a highly elaborate algorithm. It doesn't matter. It's just a process of generating this output y that you want. Okay. Now, this is what's happening when everything is exact. You don't have to worry about any sort of error, like no round-off error, no approximation error, no truncation error, none of that. This is what you'd love to do, but here's what you actually end up doing. I'll make things nicer in this case and assume that at least the input is exact. So you're still starting with the same x, but in practice that's not necessarily true either. And then your algorithm is always going to introduce some error, even if it's just due to the arithmetic. But even without that, there's other errors that could be included, like maybe you are, like for instance, if you're dealing with certain functions like sine or exponential, you're dealing with a truncated Taylor series. And as a result, you get just an approximate output y hat. Okay. Now, forward error is just the error that we've been talking about, the error in your output y. So it would be y minus y hat, or it could be so it's either absolute or relative. So there's two kinds of forward error. Okay. Now, the forward error is what the kind of error we actually care about. We want to know how accurate this is, but this kind of error can be very hard to measure. Well, for one thing, you don't know the exact value. And you may be able to come up with the idea is, since you don't know the exact value, you want to come up with some sort of bound for this error. But again, that can be difficult to try to estimate directly. So this leads to the concept of backward error. Backward error is based on an assumption about this approximation. We assume that our approximate solution is the exact solution of a nearby problem. So you can look at this from two different points of view. It's the approximate algorithm on exact input, or it's the exact algorithm on approximate input. And generally, this is a reasonable assumption. So if you have, approximation y, something that's near y, you just solved a nearby problem. And that's what is represented by x hat. So backward error is the error in x. So that could be absolute error or relative. Now, it is easier to estimate for backward error, usually. Again, like suppose x is based on measurements. You probably have some knowledge of how accurate those measurements can be. Before you plug these numbers into some elaborate algorithm, it's very difficult to determine how that error is propagated. So, if you can get to backward error, dang it, and you know how error can be amplified by whatever is going on inside f, you can just study the exact algorithm and use that to estimate the error in y. So, in other words, error analysis is often done this roundabout way because we still want to get this, we just can't go after it directly, or often it's not really practical to do. And this happens often in numerical linear algebra, as a matter of fact. You're solving ax equals b. You want the error in x. So what you do is you can estimate the backward error in a and b and use that to figure out what the error in x could be. That's something that when we talk about linear systems, which is coming up soon, you'll see illustrated. Okay, but I can give an example of error right now with regards to floating point arithmetic. So suppose we're performing some arithmetic operation, addition, subtraction, multiplication, division. So, so an assumption that is made is that the floating point representation of x op y, where y is any of these arithmetic operations, addition, subtraction, multiplication, division, is equal to the exact value times some 1 plus some error delta. So delta represents the error. And it is assumed that the size of this error is no larger than the unit round-off. So in other words, it is assumed that each individual arithmetic operation introduces an error that's no bigger than this. Now, is that always true in practice? No. What's one situation that I've already talked about where this is not true? Where a single arithmetic operation introduces error larger than this. Catastrophic cancellation, yes. So there are exceptions to this, and there are other exceptions besides that. But most of the time, and so when we perform error analysis where we're trying to account for round-off error, this assumption is still made. Okay. So what this means is, okay. All right. Now, so what's happening is if you compute a relative error, so this is the relative forward error. However, what we can also say in the particular case of addition is that the backward error in your operands error, x and y is also okay. Actually, also this delta. So it works out particularly nicely in that case anyway. But we assume that this delta is the relative error in all of these operations. And in some cases, you can try backtracking to the backward error. Or if you have knowledge of the backward error in x or y, you can try to figure out what the relative error in the operation is going to be, whether it's for multiplication or division, for instance. Okay. And that's
So
all.
does backward error, like, if you're taking a measurement and you know your measurement's like accurate to so many decimal places, is that what you mean by that estimating that?
Yeah, error in your input. So if you're taking those measurements and you're feeding that into something else to compute something based on those measurements, that error is going to propagate. And usually, whatever you do with those measurements to produce a final result, that's the error you really want. And the idea is you want to try to use your knowledge of how accurate those measurements might be, or what the error of those measurements is, to figure out the error in what's done with them. For example, suppose you have some small measurement error, but you're taking that measured value and you're plugging it into the exponential function. Then that error is really going to be amplified. And in fact, if you plug an erroneous value into a function, then the derivative of that function gives you an idea of how much that error is amplified. So in fact, differentiation is used often in error analysis. If you're trying to solve ax equals b, you often work with a perturbed b and a perturbed a, and you take derivatives of them with respect to the perturbation. You actually use Taylor series and so forth in order to figure out how much a change in a or a change in b affects the computation of your solution x. And you have to do that because you have to expect that the a and b you're using in your problem, they are probably a result of previous floating point computations which have some small error in them. And what happens to that error? How is that magnified? Or is it magnified? Sometimes error can be damped down by whatever you're doing, which is nice to have. Okay, I only have 7 minutes left. Okay. All right, I can at least start the next bit. That'll make things sound much easier. So, sorry, yes?
Oh, I was just gonna say turn the camera.
Yeah.
You got it.
Yeah, okay. Don't worry, I'm on it. Okay. At least the marker's broken in now. Behaving much better than it was at the beginning. Okay. So one very important concept that will be used pretty much throughout the semester is that of orthogonality. Okay. So a set of vectors, x1, x2, so on, all the way up to xk, is said to be orthogonal if, whenever you take the inner product of any two of them, you get 0 whenever I is not equal to j. Okay. Now, we also say that they are orthonormal if, in addition to the inner product being 0, when the indices I and j are different, that they're also equal to 1 when I and j are the same. Okay, now, this sort of situation comes up a lot, where we have some expression depending on two variables, I and j, that's equal to 1 if the indices are equal, 0 if they're not. And it happens so often that it's best to have a symbol, a nice concise symbol to represent that. So this is abbreviated by delta ij, is defined by this. So this expression, whenever I'm going to use this fairly often, it's equal to 1 if the indices are equal, 0 if they're not. And this symbol is called the Kronecker delta. Okay. Now, geometrically, when the dot product of two vectors is 0, they are perpendicular in n-dimensional space, but past n equals 3, that's pretty hard to visualize. But orthogonal is used to refer to any inner product of any kind of vectors being 0. Even if those vectors are functions, like from a function space, where the inner product would be defined using integrals. Okay. Okay, so as an example for orthogonal or orthonormal, so if I make these vectors, x is 1, minus 3, and 2, y is 4, 2, 1. So if you go ahead and compute the dot product, so you multiply corresponding components and add them up, so 1 times 4, minus 3 times 2 plus 2 times 1 is 0. So we say that x and y are orthogonal, but they're not orthonormal, because if I take x transpose x or y transpose y, I'm not going to get 1. But what I can do is I can normalize these vectors. So I go ahead and compute the 2 norm of each. Now the 2 norm, vector 2 norm, is the square root of the dot product with itself. And that's the magnitude of vectors you learned from calculus. So 1 plus 9, so square root of 14 for x. And then for y, so we have 16, 20, so we get the square root of 21. Again, square root of the sum of squares for both of these. So Now what I can do is I can define an orthonormal set. I'll let x tilde be x over the square root of 14, and y tilde is y over the square root of 21. So these two vectors form an orthonormal set because, so what you find is x tilde transpose x tilde is 1, y tilde transpose y tilde is also 1, but then x tilde transpose y tilde is 0. So you have a set of any number of vectors. They're pairwise orthogonal, but they're all unit vectors, or they're all normalized. That's where the name orthonormal comes from. Okay. One thing about terminology that's rather unfortunate is the following, that, in fact, I'm going to cut myself off because I'm out of time, because I was going to go on a rant, and I don't want to make time for that. So I'll just pick up with that on Monday and continue talking about orthogonality. Okay.
Is the product not the same as the draft filter?
It's related to that. Yeah, since the Dirac delta function is 0 for x 0. In fact, I've also seen this delta defined with just one index, and it's equal to 0 if the index is non-zero, and I guess that's part of Dirac delta. So Kronecker delta is specifically for two indices.
Okay.
Yeah.
And then the delta is for six to one, like one or
Yeah. Okay. Well, I'll hear you next week.
All right, thank you.
Yep.
Bye.
Bye.